Good afternoon, everyone. Welcome to the first session of Thinking Matters Talks. I'm Charlotte Stahl, a PhD candidate in the Department of Optical Science and Engineering, and I'll be your moderator for this talk. I'd like to begin by introducing our speaker, Dr. Gbur, who is an associate professor in the Department of Physics and Optical Science here at UNCC and my advisor. Aside from his extensive research interests into the limits of what we can do with light, Dr. Gbur has a long-standing passion for finding and making comprehensible the myriad ways that physics affects us daily. Whether it's in the classroom or on his blog, he has the instincts of a storyteller, managing to weave together the threads of history and physics, knowledge and people into amusing and informative tapestries. Today's presentation, Falling Felines and Fundamental Physics, exemplifies this talent. Whether inspired to learn the history and physics of cat turning by watching his own cats, his years of falling out of airplanes as a skydiver, or both, you can be sure to walk away from this talk having learned something new about physics and the people who study it. Please join me in welcoming our speaker, Dr. Gbur.
Okay, thank you very much. Thank you for being here. As Charlotte said, this is a talk that actually combines three things that I love to do. I love to talk about physics, I love to talk about the history of science, and like most cat lovers, I like to force people to look at pictures of my own cats. So you'll get a little bit of all of those as I go on and talk. But what I really want to talk about is a specific question related to cats, and it's a surprisingly difficult one to answer, and that is, how does a cat land on its feet, or almost always land on its feet, when it falls or gets dropped, no matter what position it starts in? And this is a problem that has really bothered scientists for about 150 years, and it still kind of bothers scientists. And that's quite interesting, and we'll look at why that is. Why is it so hard to get a definitive answer on how cats flip over? And in doing so, we'll look a bit at the history of what they call cat turning in physics. And we'll also talk about how a cat does it, or what's probably the simplest mechanism to understand about how a cat falls and lands on its feet. And that'll lead us into naturally asking, what sort of things can we learn from a falling cat? And one of the reasons that this problem has persisted for so long is there's still things we can learn from the way a cat does what it does. So let me start way back in the 1850s. And what's quite amazing about the cat turning problem, as it was called back then, you won't hear the term cat turning much these days, but back in the day, that was how everybody referred to it. But one of the first people to become really scientifically interested in this problem was James Clerk Maxwell. You may or may not be familiar with him, but he's known today as really the founder of the electromagnetic theory of light. He's the person that put together the set of equations, now known as Maxwell's equations, that describe how electricity and magnetism combine and can form electromagnetic waves, which include light, infrared light, ultraviolet, and so forth. Well, he's a very famous, distinguished physicist, but he also had a reputation for throwing cats out of windows. And as it originally started, when he was a student in the 1850s at Trinity College, he was really curious in this cat turning problem, and he kind of played around with some cats. But when he left and he became famous, his reputation changed. And when he returned to visit Trinity in the 1870s, he wrote a letter to his wife, I think essentially apologizing to her and explaining that he's not as bad as it sounds. Because he says, there's a tradition in Trinity that when I was here, I discovered a method of throwing a cat so as not to land on its feet, and that I used to throw cats out of windows. And he says, I had to explain to those people that the proper object of research was to find how quick the cat would turn around, and the proper method was to let the cat drop on a table or bed from about 2 inches, and that even then the cat lands on their feet. So he actually had to do a little bit of work to convince people that he wasn't just chucking cats out of windows willy-nilly everywhere he went. But it's very telling that such a famous physicist was interested in this problem, because there's something very deep involved in it. But it would take a few more years before people really understood how strange the problem is. And the key that got people really interested in falling cats was the advent of high-speed photography, the ability to make cameras that could take a sequence of pictures really quickly and capture the motion of animals that otherwise you couldn't tell what they were doing. Now, the most famous example of this was done by a fellow named Muybridge, Edward Muybridge, and Around the 1890s, he was the first, actually, or a little earlier in the 1870s, he was the first person to get photographs of a horse in motion. And this resolved a long-standing question about horses and how they gallop. Because if you look at pictures and paintings of horses from before this time, you'll find that a lot of them show horses with their legs stretched out in midair, or two legs on the ground and two up. And as this kind of clip that puts together a bunch of his images together shows that a horse, when it's galloping, actually has all 4 feet off the ground. And that was a big revelation for people because it was something you couldn't see with your eyes alone. You needed something better to do it. And I love this picture, which came before high-speed photography. The way that people were trying to understand animal locomotion was by attaching pressure sensors to the hooves of a horse that would string up these wires to something that a guy would hold and actually look at a meter as he rode the horse. So high-speed photography was a real game changer for biology. It really allowed people who were interested in how animals move to learn something more. Now, as far as cats go, a key figure in this study of animal motion using high-speed photography was Jules Marey. And he was the guy that did that mechanical motion picture that I showed on the previous slide. He was originally interested in animal motion and trying to use all these mechanical means. And when high-speed photography showed up, he really took advantage of the technique and built his own camera. And this is an image of one of his early cameras, which really looked like a gun. It had a trigger, it had a series of photographic negatives in a drum, and you could pull the trigger and it would rapidly whip through them and take a sequence of images in high speed. And as the years went on, he produced and he refined this technique. And by 1894, he produced the very first images of a cat being released from being held upside down and landing on its feet. And the images should be read from right to left and from top to bottom. And you can see the cat's completely upside down, and as it goes, it sort of contorts its body somehow and lands right on its feet. And this was presented in 1894 to the Paris Academy of Science. And one thing that's noteworthy about this is that Marey was not really a physicist himself. He was a fellow who was into photography and into understanding animals. So he actually caused a bit of a sort of a crisis for the attendees of this meeting at the time. Though before I mention that, I should mention that when Nature, the magazine Nature, reprinted his photographs, they added the statement about the cat's involvement in this experiment and said that the expression of offended dignity shown by the cat at the end of the first series indicates a want of interest in scientific investigation. Even back then, they pretty much figured out that cats had really no interest in doing what we want them to do. But what was really interesting is that when Marey presented his results, physicists that were present at the meeting just really didn't believe him. They were actually quite surprised. It says that a lively discussion resulted at the meeting, and the difficulty was to explain how the cat could turn itself around without a fulcrum to assist in the operation. Before Marey's photographs came out, people assumed, again because they couldn't see what was going on, they assumed that even if you were holding a cat and let it go, that it somehow managed to flip itself around by pushing off of you before it started to free fall. And I love this statement that one member declared that Marey had presented them with a scientific paradox in direct contradiction with the most elementary mechanical principles. Basically, this guy was saying that your cat violates the laws of physics if what you say is true. And this is kind of interesting, because this is an example of what I like to say is an example of what a little knowledge can be a dangerous thing. That if you know a lot of physics, it's good, but sometimes if you know a little physics, it can be worse than knowing none at all, because you think you understand things you don't really. And in this case, when you take an elementary physics class, you learn that there's certain things that are always conserved. You learn that energy is conserved. You learn that momentum is conserved. You learn that angular momentum is conserved. Ordinary momentum is sort of linear momentum. It's the sort of thing you see when billiard balls smack into each other, or when, for instance, this Newton's cradle toy is used, that the ball that hits one side, it transfers its momentum to the other side where gravity sends it back down, and so that momentum is always conserved. And similarly, angular momentum, which is really the momentum of rotating objects, we're taught that, whoops. My apologies, I haven't seen that in a while. We're also taught that angular momentum is conserved. And angular momentum, an example of how conservation of angular momentum works is you can imagine if you get on your bicycle and you start riding your bike. Well, the wheel starts turning counterclockwise, but that gives you angular momentum pointing out of the page. And because you started with no angular momentum, that means that the Earth has got to rotate the other way. It's got to get angular momentum rotating the other way. So you're actually, whenever you ride a bicycle, you're imparting a little angular momentum to the Earth. However, angular momentum is proportional to mass, so the Earth doesn't really move much when you do that, thank goodness. But it's this idea that of action and reaction. If I start something spinning in one direction from rest, then something else is going to have to spin in the other direction. And this is really the only equation I'll show, thank goodness. But we're taught in a basic physics class that the angular momentum L is basically proportional to the angular speed. The faster that something's spinning, the more angular momentum it has. And if you have a really big wheel, it's got a bigger moment of inertia and the angular momentum is larger. If you have a smaller wheel, the angular momentum is smaller. And if the mass is distributed on the outside of the wheel, it's a higher moment of inertia and a smaller one for it being distributed throughout. But this is sort of the key. In a basic physics course, you're taught that if something's rotating, it's got angular momentum. If it's not rotating, it doesn't have angular momentum. And this is what tripped up the scientists back in Marey's day, because those guys had said that this is impossible to release a cat that's not spinning and have it somehow flip over. They were thinking of this idea that angular momentum is proportional to rotation. But that only applies for rigid bodies, for things that are solid and rigid like a bicycle wheel. And as these pictures of my cat Cookie show, who's a master of non-rigidity, cats are definitely not a rigid body. I took this picture a number of years ago, and let me point out that she has a white belly. Now carefully look at this picture. She does not have a white back. In other words, that's Cookie's back on this side of her head. That's her belly on the opposite side of her head. And in the background, you can see our other cat, Mandarin, who's pretty much horrified by this whole thing. I remember the day I took this picture, I was just sort of staring at her for a while going, something's really wrong here. And then finally I realized that she was a bit messed up and took a picture, but she didn't care. But that's the thing about cats, is they're not rigid bodies, so those simple rules of how things can turn over don't really apply. And so, fortunately, to their credit, physicists of the late 1800s, early 1900s realized this, but then it became a question of how does the cat really do it? How does this cat flip over? And so there were a number of investigations. There was one done in 1922 by a German named Magnus. 1935, two fellows, Rademacher and Terbraak, did more investigations. I didn't have a very good reproduction of their images. And it went on even through the 1960s. A fellow named Donald McDonald did his own series of photographs. And people did a lot. And part of the takeaway is a lot of people were just taking high-speed photographs of cats and trying to figure out how they do what they do. Well, let me explain at least a basic idea of how it works. And I'll use my cat Sabrina here. And we'll approximate Sabrina as two cylinders. That's about the simplest model of a cat we can come up with that's non-trivial, is we'll replace her by two connected cylinders, and we'll ignore for the most part her arms and legs. And we could think about what happens if we release Sabrina, if I were to hold her upside down and let her go, which I could never actually get away with, but if I were, we could ask what would happen if she tried to flip over in various ways. Well, first of all, suppose she had her body completely straight. She could try and twist her upper body 180 degrees to get her paws facing the ground, but because of conservation of angular momentum, when she twists her upper body one way, the whole body is going to move back the other way. And unless she can constantly rotate her body in the same direction, say 360 degrees, she's not going to be able to flip over that way, because she'll have to flip her lower body to catch up eventually, and that'll just send her right back upside down. So a straight cat can't flip over. But if we imagine that the cat can bend completely, fold at the waist, then what happens? It can rotate its upper and lower body sections in opposite directions. And it can rotate them 180 degrees, and then it can open up its body again and straighten out, and where the head was, where it was upside down, now it's right side up. And this works because the angular momentum of the upper and lower body sections cancel out. They're in opposite directions. So it can twist itself, open up, and be facing right side up. Now, even my cat Cookie can't bend and rotate a full 180 degrees completely folded. But there's always a middle ground. If the cat partially bends and then rotates its cylinder parts of its body, it can partially cancel out that angular momentum of rotation and still have a net rotation of the entire body to flip over and be right side up. And I mentioned Rademacher and ter Braak before. Back in 1935, these guys actually came up with that explanation. Sort of the first really clear and elegant model of how a cat can flip over. And if we go back and look at Marey's high-speed photographs, we can actually see this in action. In figure 1, the cat is completely upside down, but its back is bent. It's got itself bent a little bit. And as it goes, it ends up turning sideways. So if you picture the upper and lower bodies as being cylinders, or body sections being cylinders, you can see that those cylinders have twisted sideways. The cat's now facing us. And so it's able to change its orientation just by bending and twisting. Well, anyway, I'll return Sabrina back into her normal state. And I love that picture of how angry she is. And she looks like that even when she's not angry. This turns out to have some practical importance. A definitive model of what's still considered sort of the gold standard of cat physics modeling was done by fellows named Kane and Scher in 1969. And the reason that they were doing it is, well, the year may be suggestive. Astronauts were going up into space and probably heading to the moon. And the idea of being able to flip over when you basically have nothing to push off of is something that an astronaut potentially needs to know how to do in an emergency, or even just inside a weightless space capsule trying to get around. So this cat research was used to train astronauts. And so here's a side-by-side comparison of a cat falling and an astronaut being dropped presumably onto a trampoline. It looks like, I hope that's a trampoline. And being able to flip over. So people can do this too. And so it turns out to be very practical. And that practicality continues. Nowadays, in the past few years, there have been a lot of robotics researchers who are trying to build and design robots that can flip over like a cat can. And this is from 2014, this is from 2013. These are just models that the research groups are using, but they're actually trying to design robots that can flip over and land on their feet if dropped from some arbitrary height and position. But if you look at these pictures, you'll note, well, that doesn't really look much like a cat. It's actually just a 3-segmented body, but kind of like our cat, we treat it as 2 cylinders. Here they're sort of treating a cat as 3 segments that can move. But even this picture isn't really the same sort of cat flipping over motion that I mentioned before. And that's part of the thing that's still fascinating about this cat physics is there's still some controversy here. This model that I showed you of the cat bending its body and twisting the segments, that's one of a couple of different strategies that a cat can use to flip itself over. And there's still some controversy. This paper was written in 2013, or published in 2013, and it talks about what they call the tuck and turn method, which is what I showed you. It also talks about the legs in, legs out method, which is the idea that, kind of like a figure skater, when they pull their arms in, they can spin faster. The idea is a cat could keep pull in its upper arms and twist the upper part of its body while keeping its legs out so that the lower body doesn't turn as much, and then repeat the process. And so there's still a debate about what role exactly the different motions of a cat play. And that brings me to something that I kind of like to use this cat phenomenon to think about. And that is, it's really sort of strange that we're 150 years in and people are still arguing about cats. Physicists are arguing about cats. And there's something really deep here in understanding why this is a problem, and it's especially useful for physics majors, but it's important for everybody, that we often talk about physics as being the most fundamental science. You'll hear a lot of snooty physicists say, well, all the other sciences, chemistry and biology, they're all secondary. Physics is the most fundamental. Well, that's sort of true that the physical laws that physicists study are the most fundamental, but there's a problem with that, and that is because physicists are looking at the most fundamental processes, they're usually looking for the simplest and most elegant explanations for problems. Now, you may notice in the real world that the real world very rarely is very simple, and that physicists actually have to work very hard to simplify problems. And things can get really hung up at times when you have a problem where there's more than one contribution to the solution, and I'll mention a few examples of that. But cats are a perfect example of that. Cats are complicated creatures with a lot of moving parts, and evolution really doesn't care about finding a simple solution to a problem. It cares about finding the most effective solution to a problem. So in a sense, there's a little bit of a philosophical conflict between reality and physics when we're trying to solve a problem like a falling cat. But let me mention a couple of other problems that seem to be like they should be really simple, but have turned out to be really hard for physicists to understand. One of which, you may have seen this toy before. It's called a Crookes radiometer. Basically, you put it in sunlight, and it starts to spin. And it was invented by William Crookes in 1873. And that was about the time that James Clerk Maxwell, who I mentioned before, Maxwell had just sort of discovered that light is an electromagnetic wave. Maxwell had also discovered that light carries momentum, that when sunlight is hitting you, it's actually applying some pressure to you. And Crookes invented this radiometer that when you shine light on it, it starts to spin. And Crookes at first said, well, this is proof that light has momentum because the light is hitting this thing and making it spin. Except that when people looked at this more carefully, they realized that it was spinning the wrong way. If it was actually the light pushing on it and making it spin, it should have been spinning in the opposite direction. Well, people started to argue about this, and 6 years later, it took another 6 years before there was a somewhat accurate explanation of what was going on. But even decades later, 1924, Albert Einstein found this a problem still worth coming back to and investigating in more detail. And I have a paper that I just printed out in my office from 1969 that has a title something along the lines of, "You don't understand how the Crookes radiometer works," because everybody keeps giving the same explanations which aren't quite correct. And one of the reasons that this is so hard to understand is just what I was saying about the cat, that there isn't necessarily a single factor that's making it turn. There are multiple factors, and they all have roughly comparable contributions to the overall effect. And that makes it really hard to try and say this is what's going on or that's what's going on. Another really amazing example is what's now called the Mpemba effect. In 1969, a secondary school student in Tanzania named Erasto Mpemba was making ice cream. And basically, to make ice cream, what they would do is they would boil milk, throw in sugar, let the mixture cool, and then throw it in the freezer. Well, one day, Mpemba was racing to get the last spot in the freezer with one of his friends. But they were both waiting for their stuff to cool, and Mpemba said, well, I'm just going to throw the boiling mixture in the freezer first so I have the spot. And his friend threw in a cooled mixture in the freezer. When they came out, Mpemba realized that the boiled ice cream had frozen before the room temperature ice cream, which is a very non-intuitive effect, and it's now called the Mpemba effect, that under certain circumstances, boiling water will freeze faster than room temperature water. And I encourage you to give it a try. It doesn't seem to always work, and it seems to depend on the water and possibly the freezer and the container shape, and that's the thing. We still don't know why this happens, but multiple factors play a role, just again, kind of like the cat problem, that it's really hard to pin down the physics of this just because multiple things contribute. And Mpemba, when he was a secondary school student, his teacher was mocking him, his classmates were mocking him, and his answer was when his teacher said, the theory says you're wrong, that can't happen, and Mpemba very wisely said, theory differs from practical, that, again, what happens in the real world is sometimes more complicated than what we see. And Mpemba's still around. He's not a physicist now, but he actually worked for decades as a wildlife manager in Tanzania and retired right around 2012, I believe. So in talking about cats falling over, it's important to note that part of the reason it's hard to explain is because it's a complicated problem. And not only is it a complicated problem, it's a problem that's connected to some really deep physics. And overall, if I were to describe what a cat does, when a cat flips itself over, what does it do? It starts in one body position, it makes a bunch of motions, it ends up in exactly the same body position, except now its feet are facing towards the ground. So we'd say it moves in a cyclic path and returns to its original position, but has a change of orientation. Well, now that people are looking for it, that same sort of property of a physical system going through some sort of cycle and having some overall fundamental change appears all over physics. It appears in what's called Foucault's pendulum. It appears in light polarization. It appears in a bunch of places in quantum mechanics. And even the Earth's wobble. The planet Earth has a little extra wobble to it that can be connected in a very similar way to this problem of cats flipping over. Now, I don't really want to lose the audience entirely, so I'll avoid the light polarization and quantum mechanics right now. But I'll mention a little bit about Foucault's pendulum. In 1851, going back a few years again, Léon Foucault demonstrated that the Earth rotates by using a free-hanging pendulum. You have a pendulum just hanging from the ceiling, and you let it swing. And as time goes on, the pendulum changes its direction. And here's a modern picture of a Foucault pendulum in a science museum in Spain, where as the hours go by, the pendulum knocks over more and more of these little levers on the side, showing that it's moving. And this is demonstrating that really the Earth is rotating underneath the pendulum. And I guess it was such a sensation back in the days that audiences would show up to just watch a pendulum swing. I'm really grateful for television and the internet myself these days. But you can see how hard it was to find entertainment back in the day. But it was a really profound demonstration. And one of the interesting things about it is it works very much like the cat system. Think about putting a pendulum right on the North Pole. Well, the pendulum's swinging, and in 24 hours, the Earth is rotated a full 360 degrees underneath the pendulum. And so if you were just standing there watching the pendulum for 24 hours straight, presumably back in the 1850s, you would see it keep changing its direction, and in 24 hours it'd be back to where it started a day earlier. Now a pendulum at the equator, if you think about it, as the Earth moves, it's not going to change its direction at all. It's just going to keep oscillating in the same direction. But if you think about it, that means that somewhere in between, a pendulum in Paris, for instance, as 24 hours goes by, it's going to be swinging. When a day passes, the Earth is back to its original position, but the pendulum hasn't gone a full 360 degrees. It's in a different position. And this is, again, very much like the cat. The cat returns to its same body shape, but it's in a different orientation. For Foucault's pendulum, the pendulum goes all the way around the Earth, but it's pointing in a different direction. And in fact, the mathematics of pendula and cats can be directly mapped. If I call the angle that the cat's body sections make with each other theta, and I call the twist of the cat's body around itself phi, I can actually draw that on a sphere, and I can mathematically directly map the Foucault pendulum problem to the cat problem. And so these are really sort of the same effect, just manifested in completely different systems. Well, let me mention just one more of these, and that's the motion of the Earth. You may know that as the Earth is spinning and orbiting the sun, the direction of the Earth's axis actually changes. It's slowly going around with a period of about 26,000 years. And no, off the top of my head, I have no idea how they figured that out either. But it's like a gyroscope. If you set a gyroscope spinning on a point, it'll circulate around. That's a precession. The Earth does the same thing. And that's shown as this circle here, showing the axis, and the circles like that. Well, the Earth also has what they call a nutation, which is as it's going precessing around, it wobbles with a period of about 18 years. Well, in the 1760s, a very brilliant mathematician physicist, Leonhard Euler, predicted that because the Earth isn't a perfect sphere, there should be an additional wobble. And that additional wobble or nutation should repeat every 305 days. And Euler was such a brilliant guy that people were feverishly looking for such a wobble with a period of 305 days and couldn't find it. It was over 100 years later that a fellow named Seth Carlo Chandler found that the period was 433 days. And that may not seem like such a big deal, but it's a large enough difference that people were wondering, well, why is there such a big discrepancy between the prediction and the experiment? Well, I can note that 1890s is when the photographs of the falling cats came out, so falling cat physics was on everybody's mind. And this is a good point to mention a little joke in the physics community, which actually goes back to what I was saying about the Crookes radiometer and the Mpemba effect, and that is that physicists like to approximate complicated systems by an absurdly simple one. And the old joke is that how does a physicist milk a cow? Well, first you assume the cow is a sphere, a perfect sphere, and ideally in vacuum. And you go from there. And that's sort of the way we try and solve problems, which works really well most of the time, but there are times that it can lead us into trouble. Well, when you get to the wobble of the Earth, well, the difference between the theory and the experimental observation is resolved the same way we resolve the cat problem, by realizing that the Earth is not a perfectly rigid body. Its outer core and mantle are semi-fluidic, so it really is an object with some sloshing around. And in fact, in 1895, another brilliant mathematician, Giuseppe Peano, he used that cat problem as an inspiration. And I love sort of the irony of this, because where I said that most physicists like to approximate complicated problems like a cow as a sphere, Peano was really going the other way around. He was saying, let me approximate a sphere by a cat. And in fact, he got into a really big argument with another mathematician that went on for about a year and a half, and it was all centered around arguing about cats. And they never really did resolve their differences. Yeah. And it wouldn't be right to not have a few pictures of cats jumping off of things. It's not really directly related to the landing on the feet, but it is sort of vaguely related, is the observation cats have other surprises related to falling. In 1987, there was a study done by veterinarians about cats that have fallen from high-rise buildings. And well, the one amazing thing is that cats that have fallen between 2 and 32 stories have a 90% survival rate, which is pretty remarkable and a little reassuring for those people that have cats in tall buildings. But the study, even more remarkably, suggested that cats are more likely to get injured if they fall from 6 stories or lower, that the cats that fell from above 6 stories tend to have less injuries than them that fall from a shorter distance. And people also don't really know what to make of this at the moment. The theory is that a cat spends about 6 stories of free fall being shocked, and then about 6 stories in is relaxed enough and sort of resigned itself, like, all right, I can relax and just take it. And that seems to be one of the prevailing theories of how they do this. So with that in mind, I could go on for another hour about cats and stuff. Like I said, I'm a cat owner. But let me just wrap up here with a couple of videos, or short videos, of falling cats in motion. And one is simply Marey's original photographs made into an animated form, so you can see the cat flipping over. And the other one is from a video by a guy who goes by Smarter Every Day. And if you look at this video, you can explicitly see the cat twist. You can see that tilted body as it bends and rotates to the side. And so to some extent, the cat problem has been solved, but there are other things, like the fact that it's stretching out its legs in weird ways, that people are still arguing how important that is in the falling motion of the cat. And I'll just leave you with that and end my talk with images of cats falling. Thank you very much.
All right, I think we have time for just a couple of questions. So if you have any questions, just raise your hand. We got about 10 minutes.
Feel free to ask. I'm not that scary, I don't think.
Could it be that the cat's vertebrae aren't as rigid as we thought, and they can just use their muscles to twist their bodies, like you said?
Sorry?
I said, could it be that the cat's vertebrae aren't as rigid as we may think, and so that they can twist their spine. They can use their muscles to twist their spine in ways.
Oh, in additional ways from what we were talking about?
Yeah.
Yeah, I mean, that's the thing is they probably, I sort of gave you the simplest sort of interpretation of how they twist and rotate. And that's part of the challenge is, yeah, I mean, different parts of the cat's spine could be twisting in different ways that are really hard to tell from an image. And this, again, is sort of a little bit of a limitation of when you start studying complicated real-world systems, and it's sometimes hard to get at the little details. So yeah, there could be additional spinal motions, other sort of motions going on that are not really obvious to see that are helping out immensely. Yeah?
You mentioned the testing done with the astronaut. Do you have any idea what height the human had to be down from?
That's a good question, and I'm not sure. I'm still doing more research into, I've had a hard time pinning down the original papers associated with this, but I'm guessing that I think he would have to be at least dropped from 10 or 15 feet in order to do it. Because humans are just, especially with the learning curve for a human to do this as opposed to a cat, yeah, I'm guessing it's a pretty good, reasonable height. Hopefully I'll know more in the future. Other questions? Anything? Cats, physics?
Cats get a thumbs up from me.
All right. All right.